Hello, and thanks for using TickBoom, a free service that helps high school students with their math problems. I've had a pretty tricky induction question sent through. So the question says the equation x squared minus x plus 1 equals 0 has roots alpha and beta, and an is equal to alpha to the n plus beta to the n for n greater than or equal to 1. So part 1 says, without solving the equation, show that a1 equals 1, a2 equals negative 1, and then a recursive relationship exists which says an equals an minus 1 minus an minus 2 for n greater than or equal to 3. So that's part 1. And then part 2 says, hence, show by induction that for n greater than or equal to 1, an equals 2 cos n pi on 3. So the word hence there gives us a clue that that recursive relationship we will show in part 1 is going to help us to then do this induction. So to start, I might just write up what we're dealing with. So we've got this quadratic, x squared minus x plus 1 equals 0. And it has roots. We're told that it has the two roots alpha and beta. And we're also given this definition of an is equal to alpha to the n plus beta to the n. And that's for n greater than or equal to 1. So that's the setup. That's kind of what we're told. So for part 1, what we need to show is we want to show that a of 1 is equal to 1 and a of 2 is equal to negative 1, and finally a of n is it kind of satisfies this recursive relationship a of n minus 1 minus a of n minus 2, and that would be for n greater than or equal to 3. And we're specifically told to show these things without actually solving this equation. Alright, so I think a natural place to start would be with a1. Let's kind of show what a1 is. Although I think before we can really get there, I think it's worth fleshing out a little bit of what we know from what we're told. So since alpha and beta are roots, what we know is they must satisfy the equation. So one thing we can say is that alpha squared minus alpha plus 1 is equal to 0, because you can put the root into the equation and know you get the solution. And we can say the same for beta. Beta squared minus beta plus 1 equals 0. And I think that's worth noting. It's probably going to come in handy. The other thing we can say for sure is that we can actually write the equation as x minus alpha, x minus beta, because when you know the roots, you can factorize the polynomial as x minus each root multiplied together. So I know that that is going to be equal to the equation that we're dealing with. Now what might be helpful is if I expand this left-hand side and then do some equating of coefficients, we can then get some more things that we know about alpha and beta. And I think these are all going to come in handy in solving for these things. So let's just expand this left-hand side. So we'll get x squared minus beta x minus alpha x plus alpha beta is equal to x squared minus x plus 1. So if I clean this up a bit, we'll get x squared minus alpha plus beta x plus alpha beta is equal to x squared minus x plus 1. And I know many people will just kind of be able to do this almost by memory, but I always find it safer to do it the longhand way, just to make sure that you don't, incorrectly remember these results. Even though they're quite common results, I'm always an advocate of, especially if it doesn't take very long, just kind of re-deriving it just to really be sure. So what we can do, we can equate some coefficients here. So we can say one thing we can know is negative alpha plus beta, which is the coefficient of x over here, must be equal to negative 1. So these two negatives will cancel. So alpha plus beta is equal to 1. I think that's going to come in handy. And this alpha beta here, we can also equate with this constant. So alpha beta is equal to 1. So I think all of this is helpful preliminary work to now kind of get into the answer. So A1, if we start with A1, a natural place to start, according to the definition, that's going to be alpha to the 1 plus beta to the 1. And as we've just shown, alpha plus beta is equal to 1. And that's what we had to show. So that's a good start, I think. For A2, A2 is going to be alpha squared plus beta squared. Now what I'd like to do is get this in terms of alpha plus beta and alpha beta, since I know their values. If I can get this into a perfect square, I think that's going to help. So we'll go alpha squared plus 2 alpha beta plus beta squared. And if I'm going to add 2 alpha beta, I'll have to subtract 2 alpha beta just to make sure I haven't changed anything. We've now, with this, got our perfect square. So that's alpha plus beta squared minus 2 alpha beta. And now I've got it in terms of alpha plus beta, which I know, and alpha beta, which I know. I might just write this over here so I don't run out of space. So that's going to be equal to 1 squared minus 2 times 1. 1 minus 2 is equal to negative 1 as required.
Panic boom!
Alright, so that's A1 and A2 done. I'll definitely have to turn over at this point to do AN. So we now want to show that AN is equal to AN minus 1 minus AN minus 2. So what I might do is just start with this right hand side and see if by expanding it I get to AN, the definition of AN. So let's just throw that in. So we'll get AN minus 1 minus AN minus 2 is equal to, remembering what AN is defined as, alpha to the n plus beta to the n. So here it would be n minus 1. So alpha to the n minus 1 plus beta to the n minus 1 minus alpha to the n minus 2 plus beta to the n minus 2. That's kind of just throwing in the definitions. I'd like to have this in terms of alpha to the n and beta to the n, because I know that's what AN is defined as. So I might just start by calling this alpha to the n times alpha to the negative 1 plus beta to the n times beta to the negative 1. And then we'd get minus alpha to the n times alpha to the negative 2 minus beta to the n times beta to the negative 2. Alright, let's factorize some of our common items. So we'll get alpha to the n times, now alpha to the negative 1 is just 1 on alpha, minus alpha to the negative 2, or 1 on alpha squared, plus beta to the n times 1 on beta minus 1 on beta squared. Now seeing it in this format, we kind of know that this part and this part both need to be equal to 1, because that's what will get us back to our definition of AN, which is alpha to the n plus beta to the n, which is what we're trying to show here. Now, I think these two results are going to help us. So that's kind of why it was helpful to just note them down at the beginning, because if we know that alpha squared minus alpha plus 1 is equal to 0, then let's do some rearranging here. We can then say alpha squared is equal to, and I'll move this over, alpha minus 1. Let's divide both sides by alpha squared, so we'll get 1 equals alpha on alpha squared minus 1 on alpha squared, which equals 1 on alpha minus 1 on alpha squared. Very good, so this part does in fact equal to 1. And similarly, using the exact same process, so I won't rewrite it, but because beta squared minus beta plus 1 also equals 0, we would get to the conclusion that 1 is equal to 1 on beta minus 1 on beta squared. You just have the exact same algebra. So both of these parts are 1, like we need. Therefore, we can say that a n minus 1 minus a n minus 2 is equal to alpha to the n plus beta to the n, which is by definition by the definition we're told, an as required. So that's the last thing we were being asked to show for part 1.
Sonic boom!
And I think it's this recurrence relationship that's then going to become useful to us in part 2. It's almost why we've been asked to go through all this work, so that we can then use it for our induction. So what I'll do is I'll turn over for part 2. So what we've been asked to do for part 2 is to show that an is equal to 2 cos n pi on 3 for n greater than or equal to 1, and this is by induction. That's the method we're going to use. Now, step 1 of all inductions is to assume, show it's true for n is equal to 1. But the tricky thing about this question, what makes it a little bit different, is actually we're going to show it's true for n equals 1 and n is equal to 2. And the reason we're going to do this is because we've got this recurrence relationship with 2 items in it, we're kind of, in our induction, going to be doing 2 items in what we show to be true and then what we assume to be true, so that in step 3, we've then got all the ingredients we need to make use of to kind of get to that third step of proving the next increment, so that then we can apply the principle of induction to kind of conclude that it must be true for all the n that we care about. So that's what makes this question a little different. It's still the same basic steps of induction, but you need to have that understanding of what you're really doing to go, actually, I'm not just going to follow the method I've been taught blindly. I'm going to think about it and realize that what I need to do is dictated by this recurrence relationship that I've just been asked to show in part 1. Alright, so let's start with n is equal to 1. So the left hand side of that would be equal to a1. And from part 1, we showed that that was 1. So from part 1. So we can see why we were asked to do that for part 1. The right hand side would be 2 cos pi on 3, because n is equal to 1. So I will just, well, cos pi on 3 should be a half, but I'll just throw that in anyway. Cos 180 divided by 3 is a half, so it's 2 times a half, which equals 1, which equals the left hand side, so that's what we needed. Alright, so that's true for n equals 1. Let's do it for n is equal to 2. So the left hand side would be equal to a2, and again, in part 1, we were asked to show a2. a2 is negative 1. So negative 1, and that's from part 1. The right hand side would be 2 cos 2 pi on 3, and that one I'll throw into the calculator. So 2 times cos 2 times 180 divided by 3 is -1, which is the left hand side, and that's what we needed. Alright, so that's part or step 1 of the induction. Now step 2, as I kind of mentioned, we're going to assume it's true for n is equal to k, but we're also going to assume it's true for n is equal to k plus 1. Again, we need the 2 steps. It makes this slightly different to other induction questions that we're used to. So what does that mean? It means we're assuming that ak is equal to 2 cos k pi on 3, and ak plus 1 is equal to 2 cos k plus 1 pi on 3. So again, we're going to make these assumptions and then make use of them in our next step to kind of trigger that domino effect that underpins what's really going on with induction. Because we start by showing it's true for some initial values, we then assume it's true for some generic values, and then through that prove it's true for the next increment. And then you can kind of, you can think about it as if, what if I let k be 1 and then we've got 2? Well, I've just shown it's true, so then the next increment must be true for 3, and then I can go on, it must be true for 4, and so on. And again, that's not necessarily the most robust way to think about what's happening with induction, but I myself find it helpful, so you might too. But in the end, we just kind of formally just say by the principle of induction. But let's kind of turn over to dig into that. So for step 3, what we're going to do is show it's true for n is equal to k plus 2, so that next increment. And if we can show this, then by the principle of induction, the result is going to hold true. So let's start with the left-hand side. What would the left-hand side of this be? Well, it's going to be a k plus 2. And this is where our recurrence from part 1 really comes in handy, because in part 1 we showed an is an minus 1 minus an minus 2. So a k plus 2 must be equal to a k plus 2 minus 1 minus a k plus 2 minus 2. So that's going to be a of 2 minus 1 is 1. So a of k plus 1 minus a of k, and notice how that is why in step 2 we needed to make the assumption for both k and k plus 1. It's this recurrence relationship. So now that we've made the assumption in step 2, ak plus 1, we've assumed to be 2 cos k plus 1 pi on 3 minus ak, which we assumed in step 2 to be 2 cos k pi on 3. Alright, now maybe it might help to simplify this a little. So let's factor out the 2. So this is going to be 2 of cos, and I might expand this, so we'll get k pi on 3 plus pi on 3 minus 2 cos, minus just the cos, I've factored out the 2 already, so minus cos k pi on 3. Alright, now this here, we can simplify, I guess, using the result of cos a plus b being equal to cos a cos b minus sine a sine b. So let's kind of make use of that trigonometric identity to expand this. So we will get equals 2, so cos k pi on 3 times cos pi on 3 minus sine k pi on 3 times sine pi on 3, and then minus cos k pi on 3. Alright, so that's going to be 2 times, and I might just throw these into the calculator. So cos of 180 divided by 3, we hopefully is familiar, is a half, so we'll get a half cos k pi on 3. Sine of 180 divided by 3 is, that's going to be root 3 on 2, and I can just check that. Square root of 3 equals divided by 2, yep. So that's going to be minus root 3 on 2 sine k pi on 3, and then minus cos k pi on 3. Now this will be 2 times, now we've got a half of something minus 1 of something, so that's going to be minus a half cos k pi on 3 minus root 3 on 2 sine k pi on 3. And these 2's will all cancel. So this is going to be equal to minus cos k pi on 3 minus root 3 sine k pi on 3. And I might stop there. I think that's fairly simplified. We could try and do more if we wanted to, but actually I think if we leave it there, all we have to do is say, does the right hand side simplify to the same thing? Now in our case, for n is equal to k plus 2, the right hand side becomes 2 cos k plus 2 pi on 3. So 2 cos k plus 2 pi on 3. So what can we do with that? I think we can use this result up here. So I'll just kind of write that as 2 cos k pi on 3 plus 2 pi on 3. So that's going to be 2 cos, well actually it's 2 times, and we're going to use this expansion because we've got a cos a plus b. So we're going to 2 cos k pi on 3 times cos 2 pi on 3 minus sine k pi on 3 times sine 2 pi on 3. So what's that? 2 times, now cos of 2 pi on 3, cos of 2 times 180 divided by 3, it's negative a half, so we'll get negative a half cos k pi on 3 minus, and then we'll get sine 2 times 180 divided by 3 is still root 3 on 2. So root 3 on 2 sine k pi on 3. 2's cancel like before, and we end up with minus cos k pi on 3 minus root 3 sine k pi on 3. And that is equal to the left-hand side.
Sonic boom!
Alright, so that is the hard work of the induction done. Now I'll just turn over to do our final formal step where we kind of state by induction what we can conclude is that an is equal to 2 cos n pi on 3 for n greater than or equal to 1. And I'd always say, don't forget that final step. Seems like kind of a bit unnecessary, you might argue, but it really is important to note the fact that we're using the principle of induction to draw this conclusion. And so you really need to understand what's going on with induction to kind of make the logical leaps that we make, especially when you hit kind of slightly different questions like this, because if all you've ever done with induction is just mindlessly followed the steps, show true for n is equal to 1, assume true for n is equal to k, show true for n is equal to k plus 1, if that's what you did here, you'd hit a wall. You wouldn't get there, because what you really had to do for this question was to kind of make the leap from the recurrence that we've shown to how you then tweak your induction steps, because we're still doing induction properly. We're just kind of making our steps have 2 bits to it in each kind of step of the induction. So instead of showing true for n is 1, we do it for n equals 1 and 2, and assume true for n equals k and k plus 1. And with those building blocks, we can then show the next incremental step and then make use of the logic of induction to draw our conclusion. So, hopefully you found that helpful. If that explanation was helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions that other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.